Everyone, my name's Chris. Oh, this is going to work. Good. And what I do is I work in the area of the Internet of Things, and I'll go into a little bit more about what that is later on. Or now.
It's now later on.
Yes. And arguably that is, at the broadest sense, all the computers that don't have screens. Computers for humans, but not for humans. And what I see the job of technology as is the gradual process of freeing humans from drudgery and fear. So I think of my job as being looking after all the computers whose job it is to worry about things that we don't have to worry about anymore. So in the process of building these things and sending them out into the world to worry for us, it's largely a case of set and forget. We build them, we deploy them once, and they go out there and do their jobs. And these are, compared to the computers we work with day to day, relatively low-powered devices. And I like to talk about, as many people do, how many times more powerful than the computers we use to go to the moon. Well, that's a figure that's fast disappearing into the ashes of history, because does everybody know what an Arduino is? It's kind of the high school student starter computer for physical computing. Cost about $3. You could rate that at maybe 8 moonshots. And then we get to things like the little computers which might be controlling your light bulbs or your internet thermostat. And maybe a couple of 100,000 moonshots or so. Raspberry Pi and its derivatives, sort of equivalent to a desktop computer of a decade ago, perhaps 30,000 moonshots. So relatively modest. They can do simple things. They can talk to the internet, most of them. They've got a few gigabytes of memory, a few gigabytes of flash storage. But they really struggle to do much with a screen or with real-time information processing, which is where we come to their aid with the cloud. We try and push the hardest parts of our computing to scalable internet compute services. But fortunately, we all walk around with a supercomputer in our pocket these days. And when you do the math, our average mobile phone nowadays could be said to be somewhere between 100,000 and 2 million moonshots, depending how you count it. But it's a lot. So what do we do with this in the IoT world? Well, we do some pretty horrible things, really. A lot of people like to joke about the Internet of Things being the worst of technology. And unfortunately, in some cases, it's true. An example I could give you is I bought some internet-controlled light bulbs, and I liked them. So a couple of months later, I went back to the same store, and I bought some more internet-controlled light bulbs of the same brand. And those two sets of light bulbs that I bought, same brand, same store, different app. Both called My Light. One's got a hyphen. One app will run one set, won't recognize the other. So if I want to turn the lights in my lounge room on, I have to think about which app does that. Times several pages of internet apps for different devices and cameras. And the apps themselves are largely comprehensively awful in terms of usability. And that's because when you're making light bulbs and selling them for $5 each, you don't really have a lot of budget to get a team of top programmers who are interested in exciting languages and getting them to go and write a nice front end that you're probably going to use once, and then have the rest of your interactions with that device through your Amazon Echo or your Google Home or whatever. So there's not a lot of incentive to build good user experience into Internet of Things. Here's another example on the web rather than an app. This is the camera I have in the driveway of my office, and it's essentially useless to me. It's not responsive. It uses some antique plugin that I don't even have on a Mac.
Is it working now? Is the camera on now?
That camera was on, not showing anything there when I took that screenshot. Yes. So when I started a business making my own Internet of Things products, I resolved to find a way to do pleasant, usable user interfaces without having to spend a fortune, without having to spend months on the job. And I settled on Elm not because I'm a functional zealot or I love purity, but because I looked at a lot of other JavaScript frameworks and went, I have to learn how many different tools. I've got a stack of dependencies as long as my arm. I just want to make a website that doesn't look like crap. And as a hardware engineer, or as someone who plays a hardware engineer on TV, I fully recognize I have no aesthetic judgment. So systems like style elements that Maxim mentioned are not very helpful to me because they rely on me having taste. So what I decided to do was outsource it to Google. I said, okay, they have this thing called material design, which is their standard, not particularly sexy, but pleasant to look at system. And there happened to be an Elm implementation of it. So this is an example. This is a system it has the same kind of processor as this in it, or a derivative of it. This is a system for retrofitting internet connections to utility metering. And it can manage up to 4 meters. You stick it in a basement somewhere where you don't want to go down there in amongst the spiders and the mud and have to read the meter manually. And then it sends all the readings up to the internet. And so you're going to need to, traditionally you would need to plug a screen into something, or you'd need to set it up at the factory and then ship it out configured. In this case, you push a button, it starts a Wi-Fi hotspot, you log on, you've got a nice little web page. Maybe it gets used every 6 months when it comes to get serviced or something, but other than that, it doesn't really do very much. And it's, yes, there's a web server running in it. We'll go a little bit deeper into that. So the things that I like that Elm gives me, and particularly this Elm library gives me, is the ability to build a single page app where I can transform the elements from display to editable, do your basic CRUD type API actions on a small amount of data. And so I can build a minimal but fairly responsive Elm UI, and especially with Internet of Things, you're probably in a basement somewhere. You probably didn't bring your 17-inch MacBook with you. You've probably got a phone. If you're a technician, you've probably got some crappy, cheap 5-year-old phone that your company makes you carry around. So the fact that I get responsiveness pretty much for free from this really makes it of value to me. And a lot of the time when you go and do the research of how do I build a single page app in Elm, you'll see a whole bunch of things that say, here's my framework, here's my skeleton, start from here. And what I find is that that's largely counterproductive. This is an example that ships with the particular library that I'm using at the moment, and it provides a separate model and update regime and view component for each page. So you have a nested hierarchy instead of having, as Maxim talked about, the Elm model where you have a model and an updater and a view. You have a top level model which simply passes updates down to one for each page. And if you were building a huge app with a huge team, you would want that. But when you're building a small app, it can be too much cognitive load to really balance the productivity. So I find that even though I almost always end up refactoring into multiple models or multiple files, I always start from one file. You in the early stages of a project to quickly chuck the ideas on the page and get there. So my typical starting point looks more like the simplest possible Elm program than the magic framework that can grow into a behemoth without refactoring. And one of the great things about Elm's compiler and its ability to basically shepherd you in the direction of correctness is that you can start with a spaghetti mess single file app and decide at some point, okay, it needs to be refactored now, and that process can be quite quick and quite painless because the compiler won't let you forget anything. So my average Elm application for a simple app with sort of 1 to 3 pages, does a few things, provides access to some information, maybe talks to some outside services, has a few API calls. Around about 1,000 lines of Elm, maybe total all assets and fonts, perhaps about 500K, which is quite easily crammable into something the size of this. Unfortunately, the particular library that I used for that screenshot I showed you earlier was based on Google's Material Design Lite, which Google in their infinite wisdom have end-of-lifed. So the author of Elm MDL said, I'm not going to bother maintaining this now that Google's jerked the rug out. Go and try this library. So Material Design Components. It's almost like the other one, but it's slightly more grey. I also ran into the fact that Elm had gone from version 18 to version 19 while I was working in the other framework, which since it's deprecated has not been updated. So I'm now forced to fairly rapidly relearn a new framework. And so I decided at the same time I was helping out some high school students with some IoT projects, and I wanted to build them a very simple framework for doing IoT that gives them the basic things they need to get one of these devices up and running. And so I gave them the basic minimal skeleton of a user interface as well. Unfortunately, the Elm MDC library is not yet officially released, so you can use it, but you can't simply do the Elm package add and magically have it appear in your tree. So I'll talk a little bit about how to work with it for now until such time as it makes it into the actual package system. And the way that I do that is I bring it in as a submodule in my Git repos, and then I set up my makefile so that when I do a build, it checks that the directory where that submodule lives. If it's got no files in it, it does a submodule update. If it's got files but no output files, it runs make in that directory. And from there on, I can pretty much not care that I'm using what's arguably an alpha library. One other thing you have to do is in the elm.json, where you specify your source directories, you can, if you're using a library that you haven't brought in via the package system, you simply add its path in there, and when you try and include stuff, it'll look in that place as well. So that gives me once again, a working front-end library that does the aesthetic judgment for me, and works quite well in an IoT environment. There are some drawbacks to trying to run Elm on a device like this. A lot of the interesting things that you can do with the web don't particularly work when you're down a hole where there's no uplink to the internet. So a lot of the things we try and do in IoT are about geolocation. And there's a huge wealth of geolocation services out there, all of which require an internet connection. So if you want to use mapping and routing and that kind of thing, you're kind of shit out of luck unless you have a fast internet uplink. And we suffer a little bit in Australia from Silicon Valley syndrome, where everything is presumed to have 100 megabits of data link all the time. And it gets way worse when you're on one of these things, and maybe you've got a low bandwidth internet connection like LTE category M1, where maxed out it's 300 kilobits. So we're talking comparable with the latter days of the modem era. Other problem is all your fonts, all your icons, all your CSS, they're all scattered through with, oh, go and get this from Google or go and get this from NPM. But I have found that it's not too difficult to go and retrofit self-containedness to these resources. So if you make a request to Google for one of their font bundles, it'll give you a CSS file that pulls in all their fonts and it'll be scattered through with other URLs. But a bit of scripting magic and we can process those down so that it's all self-contained. So if you're building a single page app in Elm, you typically have an API that you're talking to. In this case, again, it lives on the device. And C++ is not super friendly for writing web APIs. I spent quite a long time in the dirt ages writing web apps in C, and I really don't want to do that too much. But this is the future, so C++ has lambdas now. So it is possible with a bit of monkey see, monkey do, and I haven't written C++ in anger rather than sort of because I have to for quite a while, but the kind of simple JSON APIs that you need to build are doable, and if you shy away from that kind of thing, it is fortunate that when you're working with Elm on an IoT device, you can do almost all of your development off the device on your workstation. So there's this wonderful little NPM module called JSON Server, where that structure there is a representation of a data store. And all I have to do is run JSON Server on that, and it will generate an API for it. So I get a complete CRUD API where I can fetch, update, search, sort, paginate, all sorts of stuff just from an example of what my database would be. And if you're prepared to implement the same style of API on your actual device, then you have really quick and easy development process because you can run up Elm Live, which will do your live rebuilds. You run up JSON Server, which gives you a live API. You do all your work on your laptop. You can even containerize your build process if you want to. I'm in the process of switching some of my code from Elm 18 to Elm 19. I don't strictly need to use containers to do that. NPM's ability to contain its dependencies in subdirectories is pretty good. But when you start doing testing for, is this going to work on node 10 or is this going to work on some horrible cloud system that only has node 6, then the ability to quickly chuck your whole build pipeline into a container and test it there is really handy. If you are going to go and have a play with some of these things, and I will right about here, in fact, link you to the repo that has some of the code I'm talking about tonight in. The web server that ships with the Arduino runtime for these ESP processors is not great. It's enough to do a simple HTML page, but it's not multi-threaded. And despite the fact that once upon a time we all agreed that web browsers shall not use more than 2 concurrent connections, it seems that many of them no longer do that. And so the single-threaded web server works fine with Firefox, but you get random asset load failures with Safari or Chrome. So there's a, the laser's gone away. There's an asynchronous web server project which is very handy there. It's a drop-in replacement for the Arduino web server, and it does the right thing with multiple users, multiple connections. There's also a very handy little library which gives you that bootstrap process where you turn a device on for the first time. What do? It's got no keyboard, it's got no screen. How do I make it go? And there's no really great answer to that. There's all sorts of horrible hacks. There's things where you run an app on your phone and it makes beeping noises that your video camera hears through its little microphone and tells it what the Wi-Fi password is. which works really well when you're in an office environment like this on a busy day trying to provision a replacement camera and you're trying to do the beepy thing and it's not working because somebody's on the phone over there and somebody else is upset about your beeps over there. So the approach I prefer is it starts up a Wi-Fi hotspot, you connect to it, it does the captive portal thing, pops up very much like the guest Wi-Fi here. You type in your basic configuration credentials and then we bootstrap into that Elm web page that I showed you before. The other thing I would recommend is set up your devices for over-the-air update. The traditional way to work with an Arduino or similar kind of device is you're tethered by a USB cable to your computer. These days it's actually faster and more convenient to work over Wi-Fi. The one drawback is you don't get your debug output, and I'll show you some tricks to solve that in a couple of slides. There's all sorts of magic JavaScript tools that let you do cool stuff, and I don't know how to use any of them. So all I need to be able to do to get code onto my devices is to upload a file. So I have an API endpoint that accepts a file upload. I have a makefile which uploads my files and then downloads them again and checksums them to make sure they came through okay. That was the makefile side of it here. Those are the scripts. They're pretty much one line invocation of curl plus some argument shuffling. And that's really all you need to get an Elm application onto a tiny little internet microcontroller. You build your Elm code, you post-process your CSS and your external resources to remove any internet fetches and replace them with local copies, and then you just upload it all to the flash storage on your device. But I did say that the drawback of not having that cable tethering your device is that you lose the ability to get your debug output. So I wrote a set of debug macros which not only write to the serial port where you traditionally do cable-based debugging, they transmit a UDP packet in the syslog format. So if you've got a Mac box or a Unix system or even just TCP dump on whatever, you can sniff for that traffic and read the debug output as if you were cabled up. I've done a talk a couple of times around the traps called DevOps for dishwashers, and the short précis of that is you want to be able to get to the point where you can do all the kinds of automated testing that you do with your grown-up applications with your IoT stuff. So the Arduino ecosystem has always been very visual, not particularly well scripted. The good news is a couple of months ago they released a CLI engine for it, which lets you do pretty much all of the operations you need to do from a command line. So that's the TLDR of how to non-interactively build and deploy code onto an IoT device. So we built an app, we've deployed it, we've got our CI pipeline. The last thing I want to talk about is touching on things that both Maxim and Josh said about ports, which is Elm's way of talking to the outside world. So in the IoT world, the publish subscribe mechanism that most things use is a protocol called MQTT. And if you go and look under the hood of most of the cloud providers' IoT offerings, so Amazon IoT, Google's ones, Microsoft ones, you'll find MQTT down there somewhere. And there's a lovely little operating environment for IoT devices called Mongoose OS, which has runtimes for C and JavaScript, and a cloud device enrollment platform as well, that is very much like Elm. It gives you a nice capsule subset of all the things you're going to need to have a relatively safe experience in terms of taking care of all the crypto enrollment and the things that make dealing with the real world a bit of a pain. So here's an example of how to use the Payho MQTT library from JavaScript. This is the Elm side. So we set up a subscription to a port where we expect to receive a tuple that consists of a topic and a payload, which are both strings. So we've typed it strings. On the JavaScript side, we pull in our JavaScript MQTT library. We subscribe to whatever it is we're interested in knowing about. And when we get a received event, we use the port send mechanism to push that tuple of strings down to Elm. And you can do the same thing in the reverse direction where you subscribe to a port. In JavaScript, when we send to that port from Elm, we can talk MQTT. So that's kind of the next level of sophistication over a simple API, single page app. So to recap on what we've got cheap and nasty little computers, cheap and not really nasty, cheap and quite exciting little computers, which unfortunately have very little in the way of UI. So when we need to take care of them, to configure them, to manage them, we typically do that via an embedded web server. Badly in general, and I hope to be lifting the game in that area, for which I built a sort of a single page app skeleton that takes care of most of the things you're going to need, along with suggestions for API tools, for server tools, for debugging resources, and a quick précis of how to do a CI pipeline. There are slides and videos on my website, which I'll link to in a second, that will give you more information on how to do that in the long form. Final plug for myself, I also organise the Internet of Things interest group here in Brisbane. So our next meetup is in fact next Monday. So if this has piqued your interest, you're more than welcome to come along, and I thank you for your attention.
Where's that meetup at?
iLab at UQ. If you remember, if anyone of you are old UQ people, it used to be the staff club.
Where's that?
Famous University of Queensland.
Oh, okay.
Yeah. Mm-hmm. Yes. In Brisbane, people always give directions using non-existent landmarks. So you go past the roundabout that used to have the tree, you turn past the old church that burned down, you go to the building that used to be the staff club. Yeah.
Where you respawn if you die in Brisbane.
Mm-hmm.
Can this Mongoose OS thing, can that run on the Orange Pi Zero?
No.
Okay.
No. It's targeted at
Smaller.
half a dozen smaller processors.
What should I put on my Orange Pi Zero in that case?
Node-RED. Node-RED is a JavaScript environment for flow-based programming in IoT.
So if you can do JavaScript on that thing, why didn't you use Node for web server?
On this thing, the JavaScript engine is a thing called micro JavaScript. It is a quite limited subset of ES5 to the point of
Subset of
no
ES5?
promises, no. Yeah, there's no. Most of the JavaScript standard library is not there. So you have the language, but you don't have any of the classes.
Mhm.
So it's like sort of C with fewer semicolons.
So you would use WebAssembly on this one, yeah, when it comes out?
I'm quite interested. I think it's pretty much a no-brainer that Elm and such languages will quite soon retarget to WebAssembly rather than minified JavaScript. I haven't seen any information on whether it would be feasible to build a WebJS interpreter on something of this class. But there's a good chance it could be. You know, it sounds like history is rhyming again. It feels very much like the early days of Java, where everything was going to run on this virtual machine. And in fact, for those of you who weren't there the first time around, Java was originally conceived as a language for toasters and embedded systems. And then these things called web browsers came along, and some of the people at Sun kind of squinted and went, well, when you think about it, this program and this box on the screen is kind of like an embedded system, and maybe we could use the same language that we've been building to internet connect all the toasters and kettles to do these things that seem to be going to be called web pages.
JSP. Oh. Don't mention it.
Oh, I forgot the demo.
Is that why it's called Java?
Originally it was called Live Oak, and for some reason they decided they were going to rename it. Very late in the day, decided to rename it Java.
Marketing.
I think Sun paid them some money to do it.
You're thinking about JavaScript.
Yeah.
That was called something else. That was called LiveScript, I think.
Yeah.
And had nothing to do with Java, except that, yes, Sun wanted to get Java into the consciousness, so they said to Netscape, let's do a co-branding thing or something weird like that.